as it relates to critical infrastructure research. So this is what ChatGPT popped out when I said infrastructure smorgasbord, which looks pretty tasty. So we'll go from there. But yeah, the idea is there's a heap of work going on in New Zealand as it relates to natural hazards and the intersection with critical infrastructure. And what we've really tried to do, because we're a small country, we need to be as efficient as possible. There's a lot of alignment with the different research programs. So we're funded in a lot of different ways, and we need to really link together well, both to get good outcomes when we think about research, but also to make it easier for the stakeholders that we work with. We want to ensure that we have really good alignment there, and there's not a million different people talking to the same group. So really good partnership with research and industry as a result of that. So I'm just going to give a real sort of high-level snapshot overview of a range of stuff that's going on to really prompt ideas and thoughts. And if you want to know anything more, I can go into detail later on with this work. But really the way we framed it in New Zealand is that because we can access a lot of real-world data, that's where we start. So real-world data, real-world scale, real-world complexity sort of underpins a lot of the work that we're doing. As I mentioned, there's a range of different national collaborations, and these sort of symbols up here are some examples of 5 to 10-year projects that have either completed or are ongoing. And that key thing is it's across multiple institutions. So we have representations from all the different research institutions in New Zealand. They leverage and cut across the programs as well. So you add value by aligning with the different research programs, and very much multidisciplinary. Although sort of the scope here is constrained to some of the hazard and engineering, there's a much broader ecosystem that sits around and integrates through that. A big thing that's going on in New Zealand right now is we've got funding for another project from 2024 to 2031, $70 million. That's currently being scoped, and that's framed around everything related to natural hazards resilience across multiple different disciplines. So New Zealand's, I guess, interesting when we're looking at critical infrastructure to sort of set the scene is we have New Zealand's Lifelines Council. So that's a national organisation that sits at the top that really looks to try to bring together organisations across all the different types of critical infrastructure. And then if we take the step down further, if we look at the map of New Zealand there, we can see the different regional groups. And so those are regional groups focused on their regional networks, working together to try to understand what's their exposure, what's their criticality, what's the dependencies. So these different organizations work together, and then the research sort of slots. Just some pause. We're back. Research slots into that, and that allows us, I think, through the culture of collaboration in the at the industry side, promotes the culture of collaboration in the research too. So we're really lucky in that case that we get our hands on a lot of that information and data. So what I'm going to do now is then just run through some of the things that are going on from the initial point of hazards through to components to systems to dependencies, and a little bit of recovery at the end of the type of things that's going on in New Zealand. When we think first about the hazards and hazard exposure, is again, we're trying to get a better representation of the spatial and temporal characteristics of different types of hazards. And a key part of that is to try and get nationally consistent models. If we're thinking about decisions and impact and what we're going to do when we're thinking about hazards, trying to get the hazard models consistent is really key. It's not as much about being the perfect model, because there'll never be a perfect hazard model, but if you have consistent approaches to characterize hazards across the country, that allows you to have a sort of a consistent weighting or a consistent thought process when we start to think about what's next. And of course, that's both single and multiple hazards that we look at. So let's just run through a few examples. So New Zealand is, as I describe it, a land of chaos. And because of that, it's very beautiful. Without the chaos, it wouldn't be beautiful. So we like it. So the chaos creates the beautiful country that we live in. So seismic is sort of probably the front in mind of many when we think about natural hazards in New Zealand. So a lot of work to underpin national seismic hazard models that inform the design requirements. And then a lot of work then to link into nationally consistent co-seismic models. So we have examples here of landslides. So there's a lot of work to collect landslide inventory to then use to train models to create nationally consistent landslide models for the country. And so those are already in existence, And there's a whole research program to try to evolve that further year upon year. That allows you to link the shaking to those models, and then, as you'll see, to link to the so what does that impact on? In the same sense, we have national liquefaction models. So we can see examples there of maps of liquefaction susceptibility. We link that with shaking. We can create probability, or we can assess for scenarios what the liquefaction will be alongside shaking, landslides, to give this sort of the full picture of co-seismic. And we've got some work doing fault rupture hazard as well, which has been completed nationally too. So there's a lot of work in the seismic space. Tsunami, I talked about this last week at another event, but one aspect of tsunami is, can we create nationally consistent tsunami inundation models? So that can take a lot of grunt depending on the types of methods we use. So through a process of developing a geospatially underpinned model, we're able to do a national tsunami inundation model at 10-meter resolution along the coast. That's 1,500 kilometers of coastline and about 14 different return period scenarios. And using this method, just using a laptop, took about around 24 hours if you've got a multi-core laptop. So it doesn't take a huge amount of grunt, and you're able to very rapidly create those models. And we're able to compare them against different types of models. So here, sort of it performed pretty well as we would compare to our typical sort of hydrodynamic model that you would use. A much quicker, much less grunt required. And it's allowed us to explore a lot of things in relation to inundation. And so now, instead of just having maps that focus in on urban areas, we've got it along the entire coast, which can link to other aspects you wouldn't see before, like infrastructure networks that haven't been captured before. Flooding is a big issue. We had a big storm a couple of years ago in New Zealand, and the same thing. There's a research program that's wrapping up next year that'll complete nationally consistent flood models for the country based on rainfall. So for a range of different ARIs, based on developing really nice representations of each of the catchments in terms of the DEM data that we have, rainfall on grid, plus feeding in flooding characterizations through the different RISA systems, and using this method based on BG-Flood, which is an open source method, we're able to get nationally consistent flood models too. And then the last hazard here is the same thing for coastal. So from 2 to 1,000 year annual occurrence interval coastal flood events, plus sea level rise increments of 10 centimeters up to 2 meters, and accounting for the vertical land movement that affects New Zealand as well due to the tectonics. There's nationally consistent coastal flooding maps that have been developed too. And here's just an example for one small region in the country. So there's a lot of work done to try to capture all those models. What that's allowed us to do in our first real high-level cut is based on these different models that we have, try and identify in an aggregated sense, and there's many ways we can aggregate those hazards. So it's not about those hazards at the same time, it's more where do we have locations that are more exposed to those multiple hazards. And this is an example using all of the building footprints across the country, 4 million different building footprints that we have data for all those different hazards, allows us to explore in different ways that we weight them, where do we have better or worse in terms of this multi-hazard exposure. And we're now evolving this further because we've got better representations of these to understand, not just for buildings, but for infrastructure, a range of different hazards. So that's a really interesting way to explore what we're dealing with in New Zealand when we start to bring that all together. So there's a lot of work in hazards. The next piece when we're thinking about critical infrastructure is then, okay, we don't want just exposure. We want to think something about performance. So if performance in terms of damage, downtime, loss, those sorts of things, can we improve that representation of those components with the data that we have based on the events we've unfortunately had to deal with New Zealand in the past? A lot of that is underpinned by case studies. And then of course we expand that further with lab and field testing and modeling as ways for us to better represent those different network components. So bridges is a good example, and we had some work looking back. We have 10 earthquakes that have exposed the bridge stock in the past, looking from about 1960 through till present. And we have data of the shaking intensity at those different locations. And then post every one of these events, we've had field work that's gone out to assess and explore the level of performance. And so what that allows us to do is compare what we observed in terms of performance compared to what we might have predicted in the performance. And What we've really shown is we're probably quite conservative in the way that we would assess. So without the evidence from these events, we would have assumed a higher level of damage impacting on the road network. In reality, pretty much all the bridges performed well enough. There was very few that were out of service. They were significantly damaged, but they still provided a level of function. And so if you think about bridges in the context of the system, the function's really the key piece. If that can keep going, then that really influences how we perceive the performance of the transport network. So that's good news, I guess. It's always nice when things perform better than we think we do. I guess that's the conservative nature of engineers. As I said, the previous event we had in start of 2023, we had significant flooding across the east coast of New Zealand as shown there. And each of those colours is showing the locations to level of damage. So black was when you had a bridge washed away. Red is significant damage resulting in closure. And then orange requiring some level of remediation, and green, no damage. So we can see there was a large number of bridges that were impacted by flooding with debris loading, resulting in damage of those bridges. And so really nice work pulling that together. I think there was about 1,000 different bridges that were assessed there. And we have data on how performance links to different external factors. So for example, we can see in this figure here, the level of damage for the bridges as it relates to the volume of debris that built up, observed beside the bridge and the loading. And then here again, some information on the foundation type, probably not surprising here, shallow foundations and more representation of shallow foundations and the worst damage here where they were scoured away, impacting on the functionality of the bridges. So we've got this really valuable data set we haven't really even started to explore, but we'll frame up future PhD research on how we can better characterize performance of bridges under flooding. Where we don't have events, we like to go on the field and test real stuff. It's a nightmare sometimes to test real stuff, but it's very rewarding when we can. So we have a good relationship with our National Bridge Agency. And so when they're demolishing a bridge and rebuilding a new bridge, we will go out and test the bridge. So this is an example of isolated pile foundations, which we were able to test in the field before they were removed. And then this is the piers that sat above that. We decided to cut that out, ship that to the lab, and test the full-scale bridge there. And this is an old bridge, and the testing was really useful because it showed us that, again, the capacity of performance is better than we would have assessed without actually doing the testing alone. We do look to model testing. We have tsunami flume, for example, at a New Zealand scale allows us to test different aspects of infrastructure. So trying to fire a bore down of different heights and looking at how it might influence on, so for a bridge here, it would be the loading that we would transfer to then apply to computational models, or a breakwater here where we see when did the different components of that breakwater erode. What does that mean in terms of performance? We do model testing too to try and constrain those aspects. And then if we don't have case study data, we don't do lab testing in the field, then we can leverage the strong relationships we have with the infrastructure to develop vulnerability models here. And this is an example focusing on flood vulnerability and talking to the people in the industry to try to characterize what they would perceive as the performance of different components of the infrastructure across a range of different asset classes here. And the way we approached this was also to look at the expertise or the experience of each of the participants to then weight and develop, for an example here, vulnerability models where we have flood depth in one sense, but then thinking about floods depth and then linking in a maximum and minimum as it relates to the flow velocity. So flood depth, low flow, flood depth, high flow, you'll get different characteristics when you think about the percentage of damage and how you would characterize those vulnerability models. So this is work that's ongoing that allows us to feed in to characterize beyond just the exposure piece. So all that information can be used to improve our representation of components. The next piece is, and always the interesting thing for me is, you can look at these networks as a set of independent components, and that makes your life very easy. But unfortunately, that's not the case. And really, if we want to be able to understand or characterize these networks, we need to think about them as networks. So when you think about them as networks, things become a whole lot more complicated at all different levels. So we can look at exposure, which is really sort of an individual viewpoint, and loss at that network level. But the piece beyond that is to then integrate this into modeling the flow within those networks. So network flow models, be it connectivity or flow-based, so traffic simulation, for example, that allows us to add a different level of resolution, reveals different aspects around that network that you wouldn't see if you just look at it in a sort of static sense. So we've really tried to explore that in more detail. One example is with the National Liquefaction Model, is we can look at liquefaction as it relates to the road system and explore this in different ways. So we can see the map there is for the different links that have no alternate route. What's the minimum return period level of shaking that would lead to manifestation on those different links? And we can sort of highlight there the locations where that's going to trigger at pretty short return periods, or locations where it's going to trigger at quite longer return periods or not at all. And that gives us an understanding of those links of what will be the potential disruption for shaking plus liquefaction, for example. And a super complicated plot that I don't want to spend too much time describing is also thinking, well, we can use this to look for each of the different parts of the country. Each of these here is a different region, but we could look at just New Zealand by itself to start with, is for the different return period level of shaking, we can get up to a different level of the number of links or the number of segments that's going to be exposed. That's sort of an asset management viewpoint. But if we look at each individual scenario, which is the blue lines, it's a very different view as to the level of exposure of the network, be it a scenario or a plausible scenario, versus when we look at things in a purely asset management sense, there's a much larger level of exposure. So from asset management to perhaps looking at things like emergency response, how we characterize and represent the impact on the network can be quite different. And we can use these national models to help explore those sorts of things in this level of detail, which makes things quite interesting. Tsunami, I talked about the National Tsunami Inundation. That allows us to really understand what's the implications for the different networks we have in the country. So these are for airports and hospitals, for example. So the darker color is when you have a shorter return period leading to exposure. And then the lighter ones is longer return, so we can understand where those are going to be impacted. And we can aggregate things up in the national level when we're thinking about each of these hexagons as a segment along the coast. And for example, the length of road within each hexagon that's going to be exposed for a 500-year return period versus the length of rail, and have the same thing for other components of the built environment. So this national level view allows us to then start to focus in more detail on the regions that are most important for us, where we can evolve that resolution. One key system for New Zealand is our port network. All right, we're an island country, used to be many, many ports. In the past, it's reduced down. And to get from one island to the other, you have to go through ports if you're going to carry anything of level of volume. So rail and road goes between the Wellington and the Port of Marlborough, between the two islands of New Zealand. So ports are really a key system for us. They're often looked at individually as individual facilities, but really they all interact together, and we've seen that in past events. So when we look at things like tsunami, for example, and port, where we have local, regional, and distant sources, for each of those events, they're not just going to impact one port, they're going to impact multiple ports. So the system will be disrupted beyond just those individual components or facilities. So for example, here we can see for a Peru source where we have minor damage in the circles, major damage in red, and then due to the waves, and then current damage in some of these other ports, we can see that this would create significant level of disruption across that system, both to bring imports and exports out of the country and to transport people to different parts of the country following that event. And this is sort of an example as you go from different magnitudes, 8 up to 9.5 for a Peru source. For each of these ports, what's the water level, what's the current speed, when does that trigger issues for us as it relates to functionality and damage across that system. We can look at things in terms of risk with these networks, and so using the coastal flooding characterizing the damage as it relates to depth of coastal flooding, we're able to do national estimates of annualized losses to the road system based on that data. So this has been done at the regional level, but also at the national level. We can see for coastal flooding as we move from 2020 through to 2120, and we look at the annualized losses in this axis, we can see the influence of the sea level rise, different SSP scenarios, the different vertical land movement we have to deal with in New Zealand to understand what is our annualized losses look like, using roads as an example, but now been evolved this further to apply to other infrastructure networks. What's interesting when we can create or develop these numbers is what this shows us is by the time we get to about 2100, coastal flooding related losses would absorb the present budget that we have nationally for emergency works on the road. So we can link those numbers back to something that we already have in place in terms of budgeting for issues. And of course, coastal flooding is just one of the plethora of things we have to deal with when we're thinking about these emergency works. So that allows us to explore and think about what that means in the context of how we plan moving forward, dealing with these sorts of impacts. I'd said that we want to look at these systems and model them as systems. So one of the first things we did was, we realized, gosh, there's no national transport model that's actually in existence. So we used natural hazard funding as a good way to push that forward. So we developed for the South Island of New Zealand, which you can see here, a transport model using a transport modeling software, AIMSA. So that allowed us to develop a business as usual model for the South Island, as we can see here. We'll just make a pointer here. This is the South Island of New Zealand, and this is here we go. This is the traffic characterization across the South Island without any event. We started building that model in this PhD, and then about 4 months later, the Kaikoura earthquake hit and disrupted the South Island transport significantly. So not good for us as a country with an earthquake, but great for a PhD student who's developing a transport model that you want to assess the implications of a hazard event. So the student was actually able to use that case history data to check the performance of the model, and then he's applied it to other different scenarios. So for example, an Alpine fault scenario cuts off the system, changes the loading on the system, and then we can look at, as we move our way through the recovery from day 1 to day 6, what is that transport system? How has that transport system evolved as a result of that shock event? What does this look like as we shift away from that business as usual? So this model is now in place, and we've got the same thing developed for the North Island of New Zealand that's currently being integrated together that allows us to shock those systems, and based on the shock of the systems, not just give us the physical implications, but what does that mean for the reconfiguration of the transport system as we have landslides and liquefaction and shaking and impacts on bridges. So we're now running through many scenarios similar to that liquefaction scenario, but with a focus on system impacts and system response. An interesting aspect of this, as we can see here, this is that same approach, but now instead of a scenario, we're just going to take out random links of the network, and things that we've tried to then characterize as you have a loss of function of a link and it results in a detour or a shifting of that transport or a different route, increased transport distance, is how does that impact on things like emission costs? So as we disrupt different aspects of the network, it's not just the physical damage, it's the carbon implications of the loss of that system too. So we can see as we change different parts of the network, how do different aspects of emissions change? And of course, that links into that travel time as another piece that we can quantify to understand in a broader sense, what are the implications of these shocks to the system. And here we can see the implications as it relates to the different flows that these models represent. So commuters, tourists, and freight flows. Both here, the different lines here is if we were to just focus on the state highway network and ignore the local roads, or if we were going to include the local roads, that actually brings in more redundancy into the system. So the more resolution we include, the more the view shifts in terms of the implications. So this data resolution is another key sort of piece that we're thinking about when we're doing this work. Maybe a system we didn't think about too much, but it's getting more focus, has been flood defense or levees, and the linkage between the flood defense, which is run by one organization and different organizations across the country, and the dams, which are owned and run by other organizations too. So you have this interesting interplay between two quite key pieces of the function of a catchment that don't have to work together. But if they don't work together, then the implications can be significant. Or if you do work together and a flood's coming through, the way that you manage the dam and the release of water compared to the way that that flood system works, you can explore all sorts of different aspects of that. So there's a work trying to understand that system and the management and the key factors that influence that system, and then sort of looking here as how that might relate if we were to look at different aspects of the organization or functioning of the dam. Do you release small or large amounts of water out of the dam? What does that then mean in terms of the extent of the catchments that might be flooded as it relates to that management system approach? So this has been a really interesting project to try to see how those two organizations might work together. And we see that in New Zealand, flooding is a key aspect for us, notwithstanding also the performance of the levees or the stock banks as part of that. And so this is sort of an example where the extent of flooding with and without and with breaching of those levees and what that might mean in terms of the extent of inundation for those different scenarios. And then the last aspect of systems is working with electrical engineers to explore ways where we can manage the power system in different ways. And so this is an example again of an Alpine fault earthquake where there's physical damage to the network. And what happens in this case is on the west coast of that island, you can see where the shaking is highest. There's a loss of transmission network linking between the generation on the east to the communities on the west. And so this was one of the first projects where we tried to explore electrical systems modeling, where they would look to restart that network using embedded generation, and then how you would set up the protection systems of that distribution network so that it could run in what we term as an island. So island mode is where you are no longer connected to the transmission network, but you're sort of running as your own sort of separate network yourself, how that might work, and as you change to evolve that back to then linking back to the network more broadly. So that's been a really interesting collaboration, working hand in hand with the different power distribution companies. And of course, people are a network too. So this is one aspect of actually tracking where people are at any one time. So if we want to understand risk and dynamic risk, we want to know, particularly for New Zealand, where there's lots of tourists, and they don't have the sort of same pattern as the people that are commuting or living there permanently. Can we use different data sets to try to characterize where people are in space and time to then link that to the hazard models that we've been characterizing? All right, so then we've got from the individual networks, we can shift to the dependencies or the interactions between networks. And so dependencies or interdependencies, it's not always interdependencies, it's often only dependencies at one point, but the interactions between those different infrastructure systems are really key to think about all aspects of functioning. And often, if you look at a network in isolation, the implications or the decisions you make are probably not going to capture the full picture, and be it redundancies or robustness needs to actually look more holistically across different networks. So at a national scale, there's models that have been developed, collating all the different infrastructure you can see in the symbols here. And in the first instance, this work that was done by my colleague Conrad Zorn, as part of his initial work in this space, was trying to understand how things might cascade through these different networks, and understanding how much of the failures are from direct failure, how much are from indirect. And if we can see here at a national scale, if we're looking at sort of random removals, that 45% of the impacts are due to indirect implications, where there's a damage in one network that influences another network's functionality and that propagates through that network itself. So it really shows how critical the dependencies are to capture the full picture of the implications of these sorts of events. So one example here is at the national scale, looking at those coastal flooding scenarios. And what we can see here is we've got the population disruption in millions of people versus the sea level rise increments on this scale. And we have wastewater, water, fuel, and electricity networks. And the green bars are where it's really constrained by direct disruption. So the damage in the network affects that network. The blue is direct and indirect. So there's both are impacting on the function of the network. And then orange is the indirect. And what we can see for these different networks is what type of networks are constrained by those different levels of impact. So for wastewater, not surprisingly, a lot of wastewater treatment plants at the coast. So the coastal flooding impacts those treatment plants directly, thereby impacting on the functionality of the network. Water, there's a bit of a combination of two, but probably the key thing here is this fuel supply, right? So the fuel supply is clearly controlled by the indirect implications, be it impact on access due to coastal roads, being able to get to those, the impacts on power networks and so on. But the fuel supply is really, it would be, you need to look to the impacts of the function of other networks to understand the function of the fuel supply. So this allows us at a national scale to really explore what's controlling performance when we think about networks. That can be zoomed down all the way to the community scale. And so here's a few suburbs of Christchurch. We've got the maps that are showing the coastal flooding. And then we can see for each of those houses where we've got the exposure in terms of the depth of the coastal flooding from less than 0.25 meters to greater than 1 meter. And then based on a high resolution data of those infrastructure, we can then link that to where are they going to be directly exposed properties, which is these ones as shown. We can see all the other colors outside of yellow expanding further. That's where there's indirect impacts. So because of damage to infrastructure networks, we can see that these other properties of different colors might have no electricity or no utilities or no at all or no wastewater. So the level of resolution you can explore in and compare and say, look at the national scale and focus in on a key region of interest to then pick out what's controlling here habitability of those different houses. And of course, dependencies, we can delve into detail of different types of systems. So here is all the different functional system links and organizational links if we were to lose our ferry between the North and South Island as it relates to different aspects of freight. And what then leads to moves very far beyond the physical and into the organizational, the people, and all the different chains through when we're thinking about the functioning of these fast moving consumer goods and how we might explore ways that we would mitigate these impacts, again, linking together more of these aspects with the physical aspects. And then the last piece I just want to talk about is recovery. So how do systems recover? What controls this recovery? How do we test the different options? This is probably one of the key areas, I think, of more research. So we do a lot of work at time zero, but the recovery piece is, I think, where we're going to be doing a lot more work. The difficult aspect of that is there's not a lot of data to constrain that recovery, and that's really what we need to give that information. So the cyclone in early 2023, we put a lot of work into collecting as much information as we could about the functionality of these different infrastructure systems. So here's an example of the physical, so the highway damage, the disruption and recovery. We can see for different parts of the country for different dates following this, what was the level of service effectively of those different links and how that changed with time. We also are looking at the functional. So using data of freight and truck movements, we can look and see how supply chains reorganized during this event. And so we can see for different sections or segments across the island where we had reduction or increase of the movement of trucks. So how do those systems change as a result of the impact of the physical? And those two pieces are really useful for us to constrain our models to look moving forward. And we're very lucky that there's a lot more data that's collected and archived in there as it was in previous events. So this is spatial representation of the functionality of the power distribution. around the city of Napier, and you have data of how that changes sort of every day or every couple of days and how that comes back online. These are the functionality of the different ATMs, so the cash points. And from 0 to 6 days, there was areas that there was no ability to get cash out. There was no ability to pay for goods and services. It had a really significant sort of cascade beyond the road impacts and the power networks as a key, really critical service that relies on these different infrastructure. And we can see here sort of the percentage of the ATM networks that were functional with time in different parts of the country. And you can see there was areas that had a complete loss of access to cash, for example. If we're building on and developing that, we can use that further when we're thinking about aspects like tsunami. So this is now using not real events, but simulating forward events. So the city of Christchurch and the tsunami inundation, there's road, bridge, power damage, and housing damage. For the road system, that allows us to define the level of disruption of these different communities across that area, be it major to no disruption when we're thinking about access for those communities. And then working with the stakeholders, we can then start to define a recovery pathway. So how long would it take, how many days to bring those different roads and communities back online, be it less than 5 days, 10, 25 days plus, gives an idea of how you might reopen based on the damage that we've defined based on the hazard and the performance of those different components. And then you can start to test and explore different recovery trajectories and efficiencies of those. So that's a real quick fire summary of a lot of different stuff. And there's a lot of stuff going on across New Zealand, and it's really awesome to be involved in it because it's a really dynamic and collaborative community. And I think by working together across all these different things, we're building and adding and really evolving and developing our capabilities in the country. And it's from all those different aspects. I've really focused on hazard to most of the physical, but then beyond that, there's a lot more work looking at decision-making, economics, those sorts of things too. As I said, there's good collaboration. And I think the key piece is the collaboration with the industry to get the real data. And that's why really a lot of the research is very much framed around impact. And they want impact by working for us. So we have to frame impact alongside the research advances. And luckily, we're able to build that up. And the last thing I say is there's a number of PhD scholarships currently available in these projects. So if anyone has any interest, please let me know and I can point you in the right direction. And that's it. Thank you very much.
Are there any questions for me? Sure. Are there any questions in the room? Carlos.
Hi, thank you for a great presentation. I had questions about the case study that you showed of the transportation model of the South Island after the Kaikoura earthquake, I believe. So presumably there, the damage to bridges was as observed, right, in your transportation model. And I'm curious what actually happened, like above a certain damage threshold, there's no functionality in the bridge. Is there partial functionality depending on the level of damage? Could you talk a little bit about how bridge damage relates to traffic flow through those particular, links?
Yeah. So the question was about, just for the people online, the question was a little bit more detail of the transport model and representing the flow. So yeah, the idea, well, the first piece is that bridges in the South Island were the least of our worries. The biggest issue is landslides. So most of the bridges will be fine. And as we saw in the large shaking in the Kaikoura earthquake, it's the landslides either side of those routes that controlled the recovery and removing those. And yeah, most of the bridges were functional in a couple of days after the event. So the idea of the modeling for an alpine fault scenario is very much more around trying to characterize the extent of the landslides. And what we did in that work is worked with the road operators. We said, this is what the damage looks like. How would you approach recovery and how long would it take to improve these different pieces? So it didn't delve into too much more detail than that. We didn't try to really detailed model the components. It's probably more at a link where there's no alternate route, characterize the level of damage, and really it's all about timeframes. And that's really from 0 to 1 when we're thinking about that. There is work going on right now that's taking that a step further. So developing, based on all that data, we can constrain what volumes look like. And based on volumes of landslides, we can get timing and cost. And that's feeding into a model to test once we apply a scenario to the road network, give a representation of those volumes, we can start to test how we would bring different things online using a road damage recovery model.
Two questions, main questions. One is on the the consideration of multiple hazards occurring around the same time. So a flood followed by an earthquake followed by flood, is that something you're considering or planning? And the second one is what is kind of, do you see this work feeding into policy very easily, or how does that kind of interact?
Thanks for that. Yes, so the first question was about coincident cascading hazards. And yes, so there's a new research program. There is a little bit of that, but there's a new research program that's about 9 months in, and it's looking at long-term recovery and earthquake sequences. This is something we haven't thought about, as we've seen sequences in the past. If we just look at it as a single event and how we approach recovery, it can be very different if you've got a single event, and then as you start to approach this, you get aftershocks. And then not just aftershocks, it triggers another earthquake at another point. And so that's really, you'll be shaking, landslide, and then as part of that will be, because that's can be a long-term thing, it's the decadal influence of, if you landslide into rivers, you get aggregation of rivers that impacts on bridges downstream. So all those pieces and the level of flooding. So there is some work going on now where because we've got these models where we think they're good enough compared to, they're pretty good compared to our representation of components. So we might as well move forward and start to integrate them. So that's one area that we're really driving a bit more of that research program, which is really interesting. And then policy, yeah, we do a lot of stuff. We do frames decision-making for these different agencies. That we're lucky with different organizations. So for example, there's the Natural Hazards Commission, which used to be the Earthquake Commission in New Zealand. They're very active in feeding into policy. So we feed information to them. They frame that up into submissions because they're better at framing that than we will be. And then, they're always looking at that data to provide the evidence base to inform. And then when we're working with these different organizations, a lot of that is, we'll work with you. So for example, we defined a scenario for an Alpine fault earthquake that the transport agencies used to frame their decisions around how they would approach the recovery. So it's a lot of back and forward in that case. So yeah, we do see that translating, and we see the impact, and we see the decision. And I think that's why they want to continue to work with us, which is good.
Thank you very much. There's a lot to digest here. Just a curiosity about that study in which you consider several different utilities or networks, and then there is that plot which is very interesting of the entire New Zealand with the dots of different sizes. First of all, I was just curious about that plot. It's the first time I see something like that, of biaxial, this kind of interpretation of the dots. That's on one side, but most importantly, which kind of interactions did you consider in that study? What are the assumptions?
So that one was sort of a random removal study, not a scenario, but it's really to identify where are the points that if there was an impact, the degree of impact at that location is significant, but then how that then propagates spatially out through those different networks. Yeah, exactly. And that was done. It was sort of the first piece that was done. Again, colleague Conrad Zorn, who's spent some time in the UK, that was linking all the different infrastructure in any way that we could. So all those different infrastructure networks that you saw, spatially then linking where there is those linkages and dependencies was done. So it took, many years to develop that model through there. And now that's being used and evolved further. For example, the coastal flooding used that to propagate through. And we're now looking at to apply the flooding, the rainfall, the inland flooding, the same thing will be done again. So now that model's been put together, it can be used to explore the implications for various different hazards. And we're starting to think about how we build that up and represent that for multiple hazards too.
Thank you.
There are a couple of questions online. Would you like to take one
Yeah.
of those?
So the first one,
The first one is around
scarcity of data.
data. Yes.
We're working with Chilean government and other authorities developing hazards and risk maps. The big problem is the scarcity of data. How do you deal with it in New Zealand? Certainly, we've done pretty well with getting access to a lot of those different infrastructure data. Yeah, as I said, in some regions we're working with electricity distribution data, which is usually super difficult, but we discussed the ways that we can use this aggregated up to a point that it's not going to cause security issues, which is usually the big thing. And on the hazard side, I think the key thing there is accepting the level of rigor of the different models as it then relates to your application. So I think if you could spend forever trying to develop hazard models and you get to the point that you're making tiny incremental gains, whereas our representation of vulnerability and fragility of components would be way lower in terms of the level of reducing the uncertainty. So there's no point making a highly certain hazard model and linking it to a highly uncertain model and then propagating it through. You say this is going to be good enough for us to make these decisions, and it's then again scale. So if it's national to local scale, you're going to have to look at things in different ways because you're going to be more fine-grained in the decisions that you make. And then the next one there from the Netherlands. Could you briefly describe how flood events used to disrupt the network were created, particularly about the spatial dependency of flood occurrence? So that's a really good question. So that's a good question. And that's for the coastal flooding stuff, I think the question. Yes, you've highlighted an interesting aspect of that, which is that was done in a way that was highly simplified, assuming that the coastal flooding would all happen at the same time. So that wasn't looking at specific scenarios, but the idea is to start to look at that or focus in for instead of at a national level, looking at a regional level, where you're reducing down the scope and saying, okay, if you've got flooding events, they're more likely to occur regionally and affect a region rather than all of the country, and then looking at the implications of that. So yeah, that was one of the constraints of that work, but in the context of identifying the key locations within those networks that then propagated out, particularly those indirect impacts, that still was able to capture those key pieces through that work. But that's sort of the next piece, and as I described before, this difference between return period or ARI, and then between using different scenarios, particularly for an infrastructure, you sort of need to use scenarios to then explore the recovery, which is typically the key piece we're trying to understand. So that liquefaction study I talked about was one of the ways we were starting to explore what we might observe or understand if we took those different approaches.
I'm going to take Chair's prerogative and ask a question myself. It's fantastic work, and bringing it all together and having an impact is, I think, what's driving it. So I guess my question is, you're involving a lot of stakeholders, I guess, in the work. How are you doing that? And what do you find is the most challenging aspect?
Yeah, good question. So we do that in different ways. So we do that from the start. So like this new program that's being developed, they are being asked what are their priorities, and that will frame some aspect of the research program. We then also have them as partners. Some are part of the supervisory team of PhD students if they want to really get in depth of there. But we have an advisory group that evolved out of one program, and then we realized, well, we shouldn't have an infrastructure advisory group for every different research program that's different. So we've used one advisory group that all these different programs now feed into. And that's a good way to mix the programs as well as to mix them. The key issues that we have to deal with is probably how do we frame the research in a way that we target work that's not within their next 1 to 2 to 3 year timeframe. You're looking to identify the medium-term issues such that if it all works out well, by the time we work through that program, we can feed in things that aren't required in an annual basis. So really saying, this is what we can do in research, this is what you're doing in a sort of BAU sense. And if we take it in that way, then we're identifying things that they're not going to do otherwise. But we have a lot of interesting stuff. Like we've worked with different stakeholders. They've then brought in their own data scientists who then work with us, and we help frame their work program internally, feeding through research so they can then just use that. So it's sort of immediate application and implication of some of the work using or developing in-house capability, which is quite a cool new thing that's evolved.
Thank you. With that, I think we've come to the end of the questions, and maybe we can have some questions over the break.
Yeah.
Because we have another talk happening. I'm just putting the details of that. What happened to it? I would just put the details into the chat, and I don't know why it didn't go. Oh, there it is. Please join me in thanking Liam for this fascinating conversation. I have lots and lots of questions to ask after this. It's been really amazing. And yeah, I mean, happy, really want to hear about next steps, and maybe you can come and give us a presentation again soon. And yeah, and let's see the progress of this. It's fantastic. Thank you so much, Liam.
Thank you. Thanks everyone online. See you later.